Hello everyone, welcome to this tutorial. My name is Emerson Ahrari, I'm a Google Earth Engine expert. In this tutorial, I'm gonna show you how to calculate the drought severity index using GRACE Earth observation satellite. As you know, the GRACE is the satellite mission that measures the total amount of water storage, and we can understand how much water gains and loss using this data. So in this tutorial, I'm going to show you how to use the GRACE satellite to monitor the drought situation or the drought severity based on water gains and loss. So this tutorial is really useful for those of you who are interested to hydrological analysis and water resources. So if you want to learn how to do this procedure from scratch, just go to the Colab environment through the colab.research.google.com and then make a new notebook there. In the Colab, we are using Python language, and now we can connect to the Earth Engine platform through the essential libraries already developed by the Google community. So, when you make a new notebook in the Colab, now you have a Jupyter style structure there you can enter your codes. So, let's start with importing essential libraries to deal with the Earth Engine, like EE and GEE map. And another library is XEE library, but the XEE is not built-in available in the Colab environment, so we need to install and then import. Remember to add the xarray as XR. The xarray also is a suitable format or array-based format for Earth observation satellite data that facilitate uh, simply analysis on Earth observation data without any challenge. So, and remember to have the numpy as NP that is suitable for linear algebra when you are doing analysis between satellite images. So, once you're done about the libraries, let's run the cell. Now the Colab actually connecting to the servers and then importing the libraries or installing. The XEE is the only library installed, is a kind of library developed by the Google community that allowing us to combine Earth Engine image collection with X-ray format. That's really useful and revolutionary library to my knowledge, because the X-Array and Google Earth Engine, when we combine them together, then you will be able to apply numerous functions on the Python on Earth observation data coming from the Earth Engine. That's why it's really important. As you can see here, we successfully installed the libraries, and now we can clear the selected outputs just like that. Let's go to the next cell. Now we need to establish a connection between Earth Engine and Colab using EE library. EE dot authenticate first and initialize. So enter your Earth Engine project ID. If you don't know what is your project ID, just go to the code editor environment. Upper right, you will find account information. Go to the project info, and there is my cloud project ID. So you need to find yours like this and paste it into the code. The next argument is opt URL, a URL address to access to the Earth Engine. If you search about the XE and Google Earth Engine, you will find a GitHub page, a detailed instruction about the XE library. If you scroll down in this page, you will find the opt URL address. Just copy and paste into your code, just like that. After a few moments, Colab asking you permission to access to your Earth Engine account. Now, the permission granted by the users by clicking on the account information, just like that. Okay, after 19 seconds, everything settled, and we have access to the Earth Engine account. datasets, catalog, and functions. So now we can use the Python and Earth Engine capabilities for the data analysis. So before further analysis, we need to select the region of interest. Let's make a map through GEE map called the map function with a base map. For example, the train, consider it here. Let's run the map again. Now you will have a user interface. There you can find your region of interest and select by drawing tools available here. In this study, I'm gonna monitor the drought situation in Iran over the 20 years or 25 years. So as you can see here, I need to select my region of interest. First of all, we need to locate our region of interest by a marker tool. And then we need to have a marker as a shapefile or as a feature or geometry in the Earth Engine environment. So ROI or point sets to from the map, select the last feature that you draw, convert it into a geometry. There you go. You have a point address here. So in the next step, I need to call global boundary dataset and filter that dataset based on this point location. So if you search on the net about the large scale international boundary simplified version in the Earth Engine, you will find it in the data catalog page. Through the feature collection, I need to call this collection or feature collection or dataset into Earth Engine environment. So the target region is Iran, my own country. Make a tuple and paste the feature collection. Then we need to select the Iran based on actually selected points. Just define a filter bounds and filter the dataset based on a point. Then convert it into a geometry and do a simplification. Dot simplify by 1000 degree. So use the map to add layer to visualize the Iran, just like this. Let's run a cell, and after a few moments you will have the Iran border. Yeah, now there you go. The study area selected like this. It was very easy and without any challenge. So in the next step, I need to start the GRACE data analysis before actually going through the drought index. Just make another cell like this and go to the GRACE dataset in the Earth Engine. If you search about this data, GRACE monthly dataset, you will find its page on Google Earth Engine website or web page. So there is the Earth Engine snippet we can call the GRACE data based on. So now GRACE sets to paste the collection ID and define a filter bound, a filter date. These data set available since 2002 to the present or the end of the 2024. So I want to make a filter date based on, so starting from 2003 for example to 2024, 2023, just like that, only 20 years, consider it here, or 25, we can include the 23 and 24 too. So select the target band. Only one main band LWE thickness is available. This is actually correspond to total water storage based on the centimeter that shows how much water gains and loss, total water storage, how much gains or loss during months. So paste the band name, and then we need to clip this dataset based on Iran border. Make a loop structure, define a function, each image considered as IMG, then each image will be clipped based on Iran border. Let's copy properties img. We need to have the property of input images for the output. img.property names, just like that. So let's run the Grace, and after a few moments you will have a Grace data set or data collection available here. So 230 elements is available. Here you can see an image collection format. Each date total water storage dataset is available with the properties including the system timer time start that is necessary for the time series analysis in the Earth engine. So let's go to the next step. Now we need to use the XEE library and xarray to convert image collection format into an xarray format, because we want to bring this data set out from the Earth engine and import it into the Colab environment. Then we will be able to apply functions, Python functions and libraries on the satellite data processed in the Earth engine. So create a new variable like ds, and from xarray open a new data set. So the input data set is Grace. The protocol or the engine will be EE. CRS coordinate system EPSG 4326 WGS84. That's a coordinate system you can use for all around the world. The coordinate ID is same for everywhere. And also this tutorial not only limited to one single location. You can use this tutorial for all around the world. CRS, and the next is a scale, the pixel size. Scale sets to 1 because the spatial resolution in the Grace data is very coarse. It's about originally the resolution is around 300 kilometers, but here we sampled to 550 kilometer, but here I prefer to have a 100 kilometer. So the scale is based on a degree because of the coordinate system. 1 means 100 kilometer, 0.1 10 kilometer, and like that. So 100 kilometer considered here. The region of interest or geometry border will be defined through the Iran's border. Let's run, and after a few moments the dataset will be ready. So now we are converting Grace image collection into an xarray format. So in other words, we are bringing this dataset out from the Earth engine and import it into the Python environment. So that's why I say the XEE is a revolutionary library. So as you can see, the data structure changed to our point of view. And as you can see, instead of the band, we have one variable, total water storage, and also we have different dimensions, spatial and temporal dimensions available here. So, and the dataset values, as you can see, the variable values available through the time, longitude, and latitude. This is an array-based structure, and we have no access to the image format. This is an array-based structure, although we can do the image visualization here, but this structure is array-based, and we are doing the analysis based on the array characteristic. So before going further, we need to sort this data set based on temporal dimension. As you can see, one coordinate or dimension is the time. It is we have to actually sort the data based on. And remember that if you apply a simple equation, just multiply to 1 on a data set, that's the original data doesn't change, and only actually a new data set created apart from the original one, then we can actually have faster speed of processing in the next step. That's really important. It's a kind of trick, and there is no scientific reason behind it. Just here we are sorting the data and doing a very simple equation, multiply to 1, and nothing changed in the original data. Just we are making a new DS apart from the previous one. I don't know why, but it's a kind of trick that highly increases the speed of processing in the next step. Just want to share you because it's actually make everything suitable in the next step for us. So now in the next step, I need to calculate the Grace Drought Index. If you search about the Grace Drought Index or Grace Drought Severity Index, you will find several resources on the net. So for example, there is an address. Here you can see actually there is a reference we can use for the for the Grace Drought Severity Index. And also there is a category here that's helping us to interpret the final results. The Grace Drought Severity Index is calculated based on a difference between the long-term average and every month's data, and its division or divided to the standard deviation through the time. So the monthly total water storage already available by the Grace, and now we need to calculate the average and a standard deviation. So ds, it's very simple and easy to do. ds.min, we want to calculate the average through the time, and this will be ds.min, and ds standard deviation, ds.std, dimension again over the time. And now the Grace Drought Severity Index, GDSI, sets to the first calculate the differences between each month water storage and long-term average over to the standard deviation, just like that. Very simple. Let's run the cell. The GDSI is now is calculated. Let's run. The GDSI is calculated, and now we need to apply the classification based on actually the category available here. It should range from a -2 to the +2. So, and you can see there are different category and classes. So we need to do a classification based on the thresholds already addressed here. So let's make a function, and the function name is classify. We want to actually define the conditions under a function and then apply on each time data is available. So the input, we consider it as a value, the value of each time available through the matrix structure, and we want to use a if structure. So if, for example, here the value based on the category, if the value of the matrix or any value in the matrix is, for example, greater equal than 2, like this, greater equal 2.0, then we want to return, for example, class number 1. So just like that. And now we know that the class number 1 corresponds to exceptionally wet. So then we can actually consider the relationship or association between the class numbers and its description here. So, and then else if the value was greater than equal, for example, 1.6, the value is between 1.6 and 1.99, just easily write 1.6, because actually the upper value, the upper limit already defined here, so we don't need to actually add another condition. Just the base value is enough because the maximum value already defined in the previous step. So then for the second class, values greater than 1.6 and less than 2.0, we want to return value number 2, and else if but if the values are greater than equal 1.3, values between 1.3 and 1.6, return as class number 3. This is very wet class. Else if values greater equal 0.8 0.8 greater equal than 0.8 and less than 1.3, return as number 4, else if again values greater than equal, for example 0.5 and less than 0.8, return as class number 5, else if. So the next class here, you can see the next class is starting from negative values. So the lower values is minus 0.49. So, or we can say, for example, values greater equal minus 0.0 and less than 0.5, return as class 6, else if values greater than minus. Now we will have same conditions here. The rest of the conditions will be same what we had already, but their sign changed to the negative. So now you can see the next one should be 0.8, values between 0.8 and minus 0.5, return as class number 7, again values greater than minus 0.3, you can see it's same 0.3. The negative values are drought classes: abnormally dry, moderate drought, severe drought here. So for example, the values between or minus 1.3 and minus 1.59, this class actually is severe drought, and you can interpret their association. Return 8. The higher class numbers actually associated with the drought situation, and lower number or classes with the lower number showing the wet situation. So again, values greater than equal minus 1.6, return 9. This is extreme drought class, else if values greater than equal minus 2.0, return the last class, exceptional drought. So else if there else, so return, for example, 0. If we have any values out of this range, could be returned as a 0. So 0 is kind of no data, and I will show you how to convert it into a no data in the next step. So this is a function structure, and now in the next step I need to use a structure like map loop structure to apply this function on each GDSI image. Make a new variable like drought, and from xarray you can use the apply u function. The u function is a kind of a structure like .map in the Earth engine. You can actually import a function and apply it on each matrix or array available through the time in the target data set. So np.vectorize, remember to vectorize the function structure, it is very important. So, and the input image or the input array will be drought, and the last one is dusk, should be allowed here. So the input here should be GDSI, sorry, it was my mistake. So, and let's run the drought. Okay, sounds there is a problem here. I think allowed should be in a bracket structure. I hope it's fine. Okay, there is a problem here. Easily you can use the AI assistant here, or I have also a code example. I can check it out. What's wrong here? Here is dusk, and the problem still exists. I can use the alternative code to solve the problem. So dot vectorize GDSI, and also there is a description here. Now the problem is solved, but I don't know what was the problem. Anyway, the AI assistant can help us to manage somehow the errors or like this, or I can use the Control Z to see what was the differences after and before the updates. So, or we can use the example code here again. Let me to check it again because I'm curious what was the problem. Yeah, it's important to know what's the issue when you actually face with the kind of errors. So the error selected argument must be happened. I think it's not working anymore. Let's try again. Okay, we can write it again because it is important to know what was the problem. So drought xr, that's apply u function np dot vectorize classify function, and the input is gdsi dusk load. Let's try again. You can also communicate how to solve it. Oh, yeah, there is a problem here. I think we had a comma here. Yeah, now the problem is solved. Sometimes it is hard to understand what was wrong in the code, but now hopefully I figure it out. When we are dealing with the AI assistant, it is also to understand what was the problem. Try to figure it out first and then go to the next step. If you only actually use the AI suggestion and go to the next step, you will never understand what was the problem there, because here we want to learn something new, because this is our career, and maybe in a situation you have no access to any AI tools, and most of the times you need to actually rely on what you need, what you have in your mind. So it is important to learn, not only use the assistant to solve the issues. Okay, now I figured it out. I learned that the comma actually causes a serious problem inside the code, and actually the function was correct, but we had a problem a step before the function applying. So now the drought is created, drought map is created, and there is no problem here, but I need to actually replace the 0 by no data values. So here xr, call the var function and make a tuple in a drought structure, or in a drought array. Values with 0 will be replaced by none, and the rest of the values will be same as we already have in the drought. Let's run and again run the drought. Here you can see all the zero values replaced by none. So, okay, now the data set is ready, but I need to convert it into the annual format to have a better view about the annual drought in the region of interest. So, now drought with annual format dot resample is a function we can use here to convert the data frequency into the annual formats. For each year, I want to get the median value through the time. Let's run, and now we need to plot annual drought. As you can see here, 22 images with annual frequency is available. The band name is LWE thickness. This is also a variable name, but we have actually drought classes inside. Make a plot with contour based structure. X-axis sets to the longitude, y-axis sets to the latitude, call axis sets to the time explaining the temporal plot structure, and call wrap, I want to, for example, 8 plots in each row, and the next is, for example, C map or color map should be turbo here, and levels, the color levels, for example, could be 20. Let's run a cell, and after a few moments you will have, there you go, here you will have annual maps of the drought condition based on the GRACE data. The red areas and higher values, as you can see, based on the category, the higher values actually showing the drought classes. For example, the last class, the class number 10, or dark reddish areas showing exceptional drought condition or extreme drought condition. There you go. And also classes with the bluish color showing a wet situation. And as you can see in the early of 2000, you can see in the 2003, 2004 and 5 about the drought severity index, we can see we had an exceptionally wet or extremely wet situation. But as time goes, you can see the situation changed in this area, and finally we are in the very drought situation or exceptional drought situation in the most of the area in the country. So there you can find a lot of information about the data set and the drought monitoring. Finally, if you want to save the plot, remember to have the matplotlib matplotlib.pyplot as plt first, and then call the plt and save fig. So the plot name is annual drought .png format. DPI is, for example, 360, and BB box inch sets to tight. Let's run. After a few moments, you will have a new shortcut in the left panel, files, and you can pick it up from here with a good quality. Just click on the download. Immediately you can save it on your system. Open it up, and here you can see it's available with a high quality. You can check it on the situation in the Iran about the drought